Hello, everyone. Today we are going to explore the CUDA architecture and GPU machine organization. In our 372 course, we've talked about CPU microarchitecture focusing on pipelining and low latency execution. Today we are going to take a look at a parallel alternative. Before we compare hardware, we must define what CUDA actually is. CUDA stands for Compute Unified Device Architecture. It is more than just a software library. It is a hardware software co-design platform. It provides a software bridge extension to C and C++ that allows us to offload heavy mathematical work to the GPU. It provides consistent hardware model that allows our code to scale automatically across different generations of GPUs, from a laptop chip to a massive data center cluster. Before we talk about what makes CUDA special, let's take a look at the problem it's solving. Here's how you would add two arrays together in plain C on a CPU. Nothing fancy. Just a for loop that walks through every element one at a time, adds them together, and stores the result. Your CPU executes this sequentially, element 0, then element 1, and so on. One core, one thread, one piece of work at a time. For 1024 elements, that's fine. But now imagine doing this for a matrix with 100 million elements, or doing it thousands of times per second during neural network training. This sequential loop becomes a serious bottleneck. Now, here's the same exact problem written in CUDA. And the first thing you'll notice is that it looks almost identical to the C code we just saw, because it basically is. CUDA is an extension of C, not a completely different language. But look at the two things that change. First, the function has global in front of it. That single keyword is what tells NVIDIA compiler that this function doesn't run on the CPU, it runs on the GPU. That's it. That's the flag. Second, instead of calling the function normally, we call the 3232 angle brackets. Those angle brackets are the CUDA launch syntax. We're telling the GPU to launch 32 blocks of 32 threads each. That's 1024 threads firing simultaneously. Every single one of them runs the same line of code, but each on a different element of the array. There is no loop anymore. The loop has been replaced by the thread count. And this simplicity on the surface is hiding an enormous amount of hardware complexity underneath. How those 1024 threads actually get organized, scheduled, and executed efficiently is exactly what the rest of this presentation is about. To understand the fundamental machine organization of a GPU, we have to take a look at how it physically uses its silicon transistor space compared to a traditional CPU. This classic NVIDIA schematic illustrates this perfectly. Take a look at the CPU on the left. The green cores are the actual math engines. They take up a very small percentage of the total space. Instead, the CPU die is occupied primarily by the yellow control blocks and the multi-layered purple and blue cache hierarchies. The hardware budget is heavily skewed towards supporting a single instruction stream. Now look at the GPU on the right. The architecture completely flips this strategy. It strips away the massive caches and bulky control logic, shrinking them into those tiny yellow and blue bands at the edge. Removing that overhead frees up the physical silicon space to build this massive dense grid of small green blocks. Every single one of those squares is an independent ALU. The GPU intentionally trades off complex logic and giant caches to maximize raw computational space. To summarize the differences, a CPU is latency oriented. It is designed for fast sequential tasks. It uses massive cache hierarchies and complex control logic like branch prediction and out of order execution to make a single task run as fast as possible. A GPU is throughput oriented. It maximizes silicon space for arithmetic logic units. These are raw computational cores rather than flow control. Instead of predicting what a thread will do, it uses hardware multi-threading to run thousands of active threads simultaneously, using that volume to physically hide memory latencies. The GPU's fundamental building block is the streaming multiprocessor, or SM. A CPU core is built for complex sequential logic, but the SM is built for raw density to pack as many execution units as possible onto the chip. It has two critical components, CUDA cores and the register file. CUDA cores are not independent CPU-like cores. They can't fetch or decode instructions on their own. They're just math engines that the SM scheduler feeds operations to continuously. This is how the register file works. On a CPU, you have 16 general purpose registers like RBX, RAX per core. An SM has a massive on-chip register file that holds a state of thousands of threads simultaneously. This is the key. Because every thread state is always live on the chip, the GPU can switch between threads instantly with zero overhead. No saving, no restoring, just switch. That's what makes everything else work. CUDA executes instructions using the single instruction multi-threads model, or SIMT model. The hardware doesn't schedule individual threads, it groups them into warps of 32 threads. A warp is just CUDA's name for a group of 32 threads that the GPU always runs together. They run the same instruction at the same time every time. This simplifies the hardware control unit because one instruction stream drives dozens of pipelines. So what happens when a warp has to wait? Memory fetches to global memory can take 400 to 800 cycles. That's a long time to sit idle. On a CPU, this is solved with complex out-of-order execution hardware that tries to find other work to fill those stall cycles. The GPU takes a simpler and more brutal approach. It just switches to a different warp entirely. And because every warp's register state is always live on the chip, that switch costs exactly one clock cycle. No saving, no restoring, just switch. So while warp A waits 600 cycles for its memory, the scheduler has already moved to warp B, C, and D. By the time it comes back to warp A, the data is ready. The ALUs never go idle. This is also why CUDA's kernels are launched with thousands of threads, not just for parallelism, but to always have enough warps running to keep the hardware busy while others are waiting. Looking at this pyramid on the left, we can see the similarities in the memory hierarchy between the CPU and the GPU. At the top in red are registers, roughly 64 kilobytes and just one cycle to access, private to each thread, just like on a CPU. One level down in orange is L1 and shared memory at 228 kilobytes and around 28 cycles. Same idea as a CPU's L1 cache, but on the GPU, you control it directly as a programmer rather than letting the hardware manage it automatically. Next in yellow is L2 cache at 60 megabytes and around 200 cycles, acting as a buffer between L1 and main memory. In green is global memory, 80 gigabytes at around 380 cycles. This is the GPU's equivalent of DRAM, physically stacked right next to the GPU die to feed thousands of threads simultaneously. And at the bottom in blue is system DRAM at 500 or more cycles. The request has crossed off chip entirely and is traveling across the physical connection between the GPU and the motherboard. Same cache miss penalty as the GPU with an extra physical journey on top. Then the golden rule hasn't changed. Keep your data as high up in the pyramid as possible. One of the biggest performance killers in CUDA is uncoalesced memory access. And this diagram on the right shows exactly why. Look at the top warp. Every thread is jumping to a completely different memory address. The hardware can't batch those requests, so it fires 32 separate memory transactions, one per thread. You're wasting almost the entire memory bus. Now look at the bottom warp. Same 32 threads, but each one accesses an address right next to its neighbor. The hardware combines all 32 requests into a single transaction. That's coalescing, and that's maximum bandwidth. The difference is massive. Bad coalescing can slash your effective memory bandwidth by over 90%. The fix is simple. Make sure adjacent threads access adjacent memory addresses. Thread 0 reads index n, thread 1 reads n plus 1, and so on. That single change can multiply your memory throughput several times over. Conditional logic like if-else statements cause warp divergence. Since all 32 threads in a warp must run the same instruction, the hardware has to serialize branches. It runs the if path while masking the else threads, then swaps. This is why GPU optimized code avoids branching whenever possible. Finally, we measure utilization using occupancy. This is the ratio of active warps to the maximum warps the SM can support. Occupancy is typically throttled by register pressure. If your code uses too many registers per thread, the hardware physically cannot fit enough threads on the SM to hide memory latency effectively. To summarize, use SIMT for parallelism, manage your warps as atomic units, hide latency through volume, and always coalesce your memory accesses. CUDA succeeds by exposing these hardware capabilities to the engineer.